Hi all, welcome to Practical 2 of Next Generation Genomics. We're this week going to go through some assembly protocols that you will have had lectures on from Alex, and we're actually going to use some of the De Bruijn graph as a De Bruijn graph assembler as described in Alex's De Bruijn graph lecture. So again, this practical is up on Learn, so do give it a go. And next Monday we will have some discussion sessions to talk about any problems you had. We also have the discussion board as well, always live, so you can pick our brains as we go through, as you work your way through those practicals. So, practical 2. Our objectives for this, as I say, is to use a De Bruijn graph assembler. But we're going to do a little bit more than that. We're not just going to make an assembly and be done with it. We're actually going to make an assembly and really get into the nitty-gritty of what the parameters mean. And whilst we're doing so, share the results of those tinkerings with our classmates. So, our practical objectives for this week. Firstly, log into the bioinformatics server, which hopefully you should all be quite familiar with now. We'll then create a link to the data we're going to use for the practical. Like we did last week, we're going to use soft links to link to data that's stored on the server, so we don't all have to have the same copy of our data. We'll then use the now familiar FastQC to assess the quality of these data. And we'll do that before we go on to our assembly step. Now, this time around, we're not going to go through a trimming process or anything. These reads are in pretty good shape, but we want to just double check and see if there are any problems there before we go on, as we would do with any protocol in the future. So we'll then go on to using a De Bruijn graph assembler called Velvet, which assembles short reads into longer fragment contigs. We'll then play around with those assembly parameters and see what effect those parameters have on the number of contigs we get and the length of those contigs, and essentially how good an assembly we've made. We'll then use an aligner to map our reads back to assembled contigs. This means we can go back and look at where our reads map to with a genome viewer called IGV. So the assembly tool, as I mentioned, is called Velvet. It's maintained by the EBI, so the European Bioinformatics Institute. It is a De Bruijn graph assembler that works in two parts. So it consists of two commands, Velvet H for hash and Velvet G for graph. So Velvet H creates a hash table, which is a way of indexing the k-mers that are created. And once that's done, we have a fast access table of k-mers that we can then construct a De Bruijn graph from. That De Bruijn graph is then tidied and errors are corrected before our contigs are given back to us. Now, Velvet produces contigs, and we'll see how our parameters affect what contigs are created. But it also means that we can use paired end information from our reads to join those contigs back together. We can scaffold them together to see if contigs actually join together. So you'll be aware that we have paired end information for reads, and if we've got one read mapping to assembling in one contig and then one read assembling in another contig, we can use that paired end information to scaffold those two contigs together because of that extra information that we have. So there are a few different parameters we can decide upon when making our assembly. We can decide upon the k-mer length, and we can put on various other filters. And throughout the practical, we're going to ask you to toy with these parameters a little, and then share the results onto a Google spreadsheet. This way we can see exactly how these different parameters affect our assembly. So don't feel constrained to using the exact parameters that are laid out in the practical. Please do feel free to kind of mess around with things, as you can't break anything. So just be inquisitive and have a go with some different parameters, maybe even ones that you think are going to give you bad assemblies. It's all interesting information because we're, as I say, going to share the results and see what contigs created. In order to make that assessment, we are using a utility script which was designed by actually a former bioinformatics MSc student, Sujay, who has written a small script to give us some statistics back on how well our assembly has worked. So once we have our assembly, we can also map back to our then created assembly our original reads. So we can map our reads back to our assembled contigs and see how it all pieces together. Now when we do that, we're going to create some new file formats, some of which you may or may not have come across before. So I just wanted to give you a quick rundown of those particular file formats, just in case these are brand new to you and you're coming across them for the first time in this practical. The first one is the sequence alignment map, or SAM file. Now SAM files are a representation of how well reads map back to a reference. Now you can see in this example that we have different reads in different rows. We have 1, 2, 3, 4, 5, 6 reads mapping back to our reference at the top. Now SAM files contain the information about how well this mapping process actually worked, and the information is largely encoded. So we have we have the name of the read that's mapping. We have a flag, a bitwise flag, which we don't expect you to know off the top of your head. If you're interested in what these mean, you can go to the European Bioinformatics Institute website and look up what these flags actually mean. Generally, they're to do with how well the pairs of reads have mapped, and they give us an idea, encoded idea, of how well that process worked. Also in there we have the position of where the mapping, where the read mapped, so essential bit of information. We also have this thing called a cigar string. Now the cigar string is a way of encoding what positions within our read mapped, which didn't. Let me elaborate on that now. So cigar strings, in this example, we've got our reference genome here, and we've got a read mapping along the bottom. Now cigar strings are actually relatively straightforward in terms of the way that they encode this information. So if you see our cigar string here at the bottom and our read mapping here in the middle section, we have 3 bases aligning perfectly to our reference. So we have 3 matches. It's represented by 3M. We have then one base in our read that is not present in our reference. Now this is an insertion, so we have one insertion. We then have 3 bases mapping, so another 3M. We then have one base in our reference that isn't represented in our read. So this is a deletion potentially in relation to our reference. So we have 1D, one deletion, and then 1, 2, 3, 4, 5 matches, so 5M. So that's cigar strings, actually relatively straightforward, relatively intuitive way of mapping or representing that alignment. Now you may also come across BAM files. BAM files are essentially all the same information except compressed. So whereas SAM is our sequence alignment map, BAM is a binary alignment map. And as you can see, it's not particularly human readable. It's all of that information compressed into a computer readable form. And so generally this is the way that we store that information as a compressed form. SAM files can be very large if you imagine the kind of data we're working with. So BAM files are actually SAM files, smaller brother, but much more common really in terms of working in bioinformatics because they take up that much less space. So all of that information you can see is kind of stored somewhere within this kind of large cloud of gibberish, but all of that same information from the SAM file that we saw in the different columns of our SAM is still stored in our BAM file. So those are a couple of the file formats that we're going to come across, and as I keep mentioning, we are also going to share our results. So as you're working through, you'll see a link to this Google spreadsheet. Now, I've kept up last year's practical results because it's actually nice to build a bigger data set. So I'm going to keep this running. So please just add your data into the top of this, insert a row and enter your parameters and the statistics that you get back out from our scaffold stats utility script. And as you do that, you'll see your data is added to a graph, and we can see exactly how our different parameters, our different k-mer lengths, whether we're using paired end or single end data. So we can see how that affects the number of contigs we get in our assembly, and ultimately how good an assembly we're going to get at the end of the day. So that's just should hopefully be a bit of fun. Once you've got those numbers, it gives you a comparison as to what the other parameters do as we go along. So as always, the practical document is set out in the same way. So we have instructions in bold. Any text in boxes is generally code that needs to be entered into the command line. And we've also highlighted some tips in pink as well. So same format as we had last week. So please do have a go at this. And again, we will be going through this in discussion sessions on Monday at 11 and then 4. And any questions in the meantime, please do get in touch with us on the Learn discussion board. And yeah, we look forward to seeing you on Monday. Well,